plenary speaker, which is Marcia McNutt. She's a geophysicist and currently president of the National Academy of Sciences. McNutt began her academic career at MIT, where she directed the Joint Program in Oceanography and Applied Ocean Science and Engineering. She served as president and CEO of the Monterey Bay Aquarium Research Institute in Moss Landing, California. During her time there, the institute became a leader in developing biological and chemical sensors for remote ocean deployment. It installed the first deep-sea cabled observatory in U.S. waters, and it advanced the integration of artificial intelligence into autonomous underwater vehicles for complex undersea missions. She became president of the American Geophysical Union. Was there from 2000 to 2002. Was director of the USGS from 2009 to 2013. During her tenure as director, the USGS responded to a number of major disasters, including earthquakes in Haiti, Chile, and Japan, and the Deepwater Horizon oil hemorrhage in the Gulf of Mexico. She led a team of government scientists and engineers at BP headquarters in Houston who helped contain the oil cap and the well. Helped contain the oil and cap the well. There we go. For her contributions, she was awarded the U.S. Coast Guard's Meritorious Service Medal. From 2013 to 2016, she served as editor-in-chief of the Science family of journals. Her honors include the American Geophysical Union's McElwain Medal for research accomplishments by a young scientist, the Maurice Ewing Medal in 2007 for her contributions to deep-sea exploration, and membership in the American Philosophical Society and the American Academy of Arts and Sciences. Her presentation today is titled Energy Transformations to Meet the Climate Challenge, Advice from the National Academies.
I am so pleased to be here, able to present to this wonderful audience at MIT. I regret that we can't all be together, but I'm sure this is a much safer route. This is a very important topic that MIT has chosen to tackle this year, the issue of climate change and energy. The material that I'm going to be presenting to you today is, of course, not my own work, but it is the combined work of a number of very distinguished committees who have addressed these questions on behalf of the National Academies of Science, Engineering, and Medicine. And the title of my presentation is shown here on this slide, Tackling the Hard Stuff, Game Changers in Climate and Energy Systems. So if I can get these slides to advance here, which we don't want to do. Here we go. Here are my key messages, just so that you know where this talk is going. And if any of you tend to nod off in the presentation, you'll know where I'm going to end up. I've got 5 key messages for this presentation. First of all, we are literally cooking the planet with global warming. And today's energy system is the biggest source of emissions that are causing climate change. The good news is we can make some easy changes today. We've got technical solutions that are known. But some of the parts of the problem will be hard, either for technical reasons or because of the challenges in people, processes, and institutions. And in my view, the technical problems may actually be the easier ones to solve, that the people problems, the process problems, and the institutional problems could be the more difficult ones. And fourth, we need to invest in developing game-changing solutions that, with some luck and ingenuity, can help us make those hard problems seem easy. And finally, we will go further and do better if we include all people in our approaches. Okay, now this is a familiar picture. It is the lights as seen from space. And the problem is, while energy, we all agree, is terrific, it allows us to have our quality of life and do the work we want to do, but fossil energy does pollute. As we can see from this slide, these are pixels from a NASA image. We see strings of cities and also the transportation networks that connect them. We even see from space gas flaring, from oil and gas development. Energy use is essential, but our modern energy system is polluting our planet with greenhouse gases. Now, let's start with the easy stuff. There are 3 things we can do today that are low-hanging fruit. We can decarbonize electricity generation, and along with that, we can electrify more end uses. And third, we can reduce energy demand while increasing value, comfort, and convenience. And I'll give you some examples of all of those. First of all, what we can do today to decarbonize energy generation. These are some examples where fossil fuels are burned for space heating, water heating, industrial processes, releasing CO2. Some of these processes are relatively easy to electrify, including space heating in homes and businesses via electric heaters, heat pumps, and heat and power. We can also go to wind energy, solar energy, etc., in order to decarbonize electricity generation. We see a nuclear power plant here, which is also, of course, a carbon-free method of producing energy. Furthermore, this is a map that shows of how we can electrify end uses. This is just an example of building heat that shows across the US the different kinds of building heat that is in use today. You see in the Northeast that it's largely fuel oil or other, which is probably wood stoves, etc. Whereas in the Southeast, it's already mostly electric, as well as in the Pacific Northwest. Through the Midwest and parts of California, we have LPG, and in many areas, there's also natural gas that's piped into homes. So this shows that we have a lot of room to grow in terms of electrifying just building heat. Now, also among the easy stuff is reducing energy demand, for example, through efficiency. Now, this plot shows in the blue line on the top how from 1972 up to 2016, which is on the right, how the volume in cubic feet of refrigerators has increased. Not a lot, but to some extent. At the same time, the energy demand from those refrigerators has dropped precipitously from, in the units here, 2,000, and the units are kilowatts per year, down to a quarter of that, down to 500. And at the same time that the energy demand from those refrigerators has plummeted, so has the price. So this is a win-win-win situation. We can have bigger refrigerators that use less energy at lower cost. And you can imagine that this type of curve can be replicated with other electric appliances. Oops. Now let's move to some of the hard stuff. Let's look at the technically hard stuff. Technical challenges remain significant for distributed emissions in transportation, in agriculture, for intense duty cycles like freight and air transport, and in high temperature industrial heat, and for the greenhouse gases released as part of chemical reactions, for example, in producing steel and cement. These are all areas which are much more difficult to find easy solutions for. And there's also logistical challenges. Even when technologies are known, logistical challenges lie in building out the infrastructure, in implementing technologies because they cost more upfront than the higher carbon emitting technologies. And also there are logistical challenges in motivating consumers when they have no financial incentive to purchase a lower emitting technology. Right now we've seen low fossil fuel prices, which leave little consumer incentive to switch to, example, to renewable electricity. So how much is reasonably easy with the technology we have today? Well, surprisingly, about 70% we can do with technology we have today. The easiest stuff is about 30% of emissions, which is decarbonizing electricity generation and efficiency improvements. The moderately easy stuff is another 40%. For example, light duty vehicle transportation, some building and industrial electrification. So that leaves only about 30% that is hard to do with the technology we have today. And so focus has to be on developing the game-changing technologies to make it easier, and that should be the focus for investments to provide our future options. So let's look at game changers to take the US to zero net emissions. So people need energy to do almost everything they want to do. Investment in research and development of new technologies can give us options to use energy to reduce emissions to zero. Growth in institutions, people, and processes can facilitate the development and commercialization of those technologies in the market. But there are challenging problems in distributed emissions, the difficult duty cycles, which I mentioned, and developing solutions in technologies, institutions, people, and processes. Those are where we need the game changers. So where might we look for some of these game-changing technologies? We can look in algorithms and other means to maintain grid reliability with intermittent renewables. We know that the sun isn't always shining, the wind isn't always blowing. How do we compensate for that? We need to look at advanced nuclear electricity generation. I don't have to repeat to this audience what the concerns are about the current generation of nuclear power plants. We can look for net zero carbon liquid fuels, and I'll talk a little bit more about that, and negative emissions technologies, which I'll also talk more about that. So algorithms to maintain grid reliability with intermittent renewables. So renewable generation is one of the major keys to decarbonizing the grid, but it represents reliability challenges and the need for storage, better batteries, for example. But algorithms can provide functionality to maintain safety and reliability. There's the potential to create, for example, something called virtual storage through coordinating building loads, EV charging and discharging, so that we don't have to actually really store things, but just balance the load in ways such that we're smart about how we use that renewable energy. And we can use machine learning with self-improving algorithms and artificial intelligence. That all has future potential. But all will necessitate cybersecurity considerations and improvements. We've all heard of some of the hacks on power generation facilities and how vulnerable we can be to those. So we can't forget about cybersecurity. Now, grid integrated buildings offer the ability to shift electrical load to meet supply. So we imagine the old days where a building just connected to the grid and it pulled power from it. Now, grid integrated buildings are smartly integrated to the grid such that they are efficient, they're connected, they're smart, and they're flexible. They are persistent in their low energy use. They minimize demand on grid resources and infrastructure. They're also connected two-way with flexible technologies to the grid, between the grid and the occupants. They're smart. Analytics are supported by sensors and controls that co-optimize efficiency, flexibility, and the occupant preferences. And they're flexible with loads and distributed generation storage can be used to reduce, shift, or modulate energy use. You imagine one person in an office is always too hot, the person in the office next door is too cold. There's no need to turn on the air conditioner for one person and the heater for the other person if you can balance the heat appropriately. Now, advanced nuclear electricity generation is also an important thing to look at. I haven't seen any route to maintaining below 2 degrees global warming that doesn't involve continuation of nuclear power generation. Nuclear is currently 20% of the generation of power in the US. And the important thing about nuclear is that nuclear is almost always on. If you look at the capacity factor by the different source, nuclear has the highest capacity factor of all of the other energy sources, meaning that nuclear power plants are producing close to maximum power more than 93% of the time, whereas natural gas is only at 56%, coal at 47%, hydropower 39%, wind 34%, solar 24%. And wind and solar have such low factors of capacity because of the amount of time the sun is shining and the amount of time the wind is blowing. So if you need to replace nuclear with other no carbon sources, you have to create a lot of solar and a lot of wind to replace that nuclear. Now, if you look at US electricity generation by source on the right side of the slide, you see that nuclear is kind of slowly projected to decline in the future, while non-hydropower renewables are projected to go up, but they have to go up a lot to compensate for any loss in nuclear. Furthermore, if you look at the age profile of nuclear power plants in the US, with the United States on the top, the red bar is those plants that are over 30 years old, and the blue is less than 10 years old. You see, for example, compared to China, how old our fleet of nuclear power plants are. If we don't look at renewal of nuclear generation very soon, we will be rapidly losing capacity of a type of power that produces no net CO2, or actually no CO2. So advanced nuclear electricity generation is an area of intense research right now. Now, the Nuclear Regulatory Commission regulations are based on what are called light water reactors. And these are basically glorified steam producers. The reactor core heats circulating water that ultimately becomes steam, that rotates a turbine, that generates electricity. These reactor designs have very high capital costs, long deployment timelines, and large space requirements. They must abide by rigorous safety regulations, and they cannot be close to high population areas because of that. Thus, they require large investment in transmission infrastructure to get the power from their siting to where it's needed. Now, advanced nuclear electricity generation has to compete with natural gas right now if it's going to be economically viable. This diagram shows the net additions and retirements in natural gas as compared to nuclear. Now, the solid brown bar shows the new natural gas power generation that's gone in, and the stippled brown, the ones that are projected. The dark blue, or the solid blue, shows mostly nuclear retirements and just like one addition. And the stippled blue shows a few nuclear additions, but mostly nuclear retirements that are planned. So you can see that it's quite obvious that nuclear is having a very hard time competing with natural gas. That makes the future of nuclear very uncertain, and marketplace concerns are the biggest problem. For this reason, new reactors are being designed as small modular reactors, which have nowhere near the space requirements of traditional reactors and therefore lower capital and safety costs. Many have passive safety features, meaning the reactor does not require any active intervention or electrical feedback in order to bring the reactor to a safe shutdown. Some designs are currently being considered by the NRC, and demonstration projects are underway. Most notable is the NuScale system, which will be demonstrated at Idaho National Lab with buy-in from Utah Associated Municipal Power System. So here's what in advanced nuclear electricity generation, the small modular reactors looks like. They have a pressurized water reactor, and they have lower capital costs. They're factory assembled, small siting requirements, and passive safety features. Now, here's the various generations. Now, Gen 2, which are the pressurized water reactors, the boiling water reactors, are already built. Gen 3, there are some that have been built by Westinghouse in China and the US. They have a simpler design. They have, but they're still boiling water reactors. The NuScale ones, which are the ones that are on the drawing board now, are furthest along in the regulatory process, but many other advanced reactors are in the works. These Gen 4 designs operate at higher temperatures, and they're using cooling media other than water. DOE recently announced the Advanced Reactor Demonstration Project, which aims to help some of these unique designs reach demonstration and potential commercialization. So these Gen 4 reactors are different. The regulatory landscape may have to be completely overhauled to accommodate advanced reactor concepts because of the difference of different cooling media and different types of fuel, most notably high assay, low enriched uranium, which is an enrichment level that currently isn't available in the US. And many advanced reactor companies are considering economic viability to be their #1 priority. So many are also designing their products to be small modular reactors with potential alternative applications and ability to cooperate with renewable energy sources. So in other words, when the sun isn't shining or when the wind isn't blowing, they're working in tandem. So let's go on to net zero carbon liquid fuels. Net zero carbon liquid fuels use water and captured carbon dioxide or waste biomass and renewable energy to generate liquid fuel replacements for fossil fuels. The fuels can be stored, transported, and used as needed. And when burned to do work or provide heat, these fuels release only the carbon dioxide originally used to make them. So it's a net zero carbon cycle. The net zero carbon liquid fuel process will use more energy than direct use of fossil fuels or electricity. So the uses are probably best when a liquid fuel is needed, and that's going to be prioritized, because in addition to the energy from the sun to grow the plant feedstock, you also need to use solar energy to make the liquid fuel. So there's sun's energy or wind energy or whatever used at 2 places in this cycle. So there's probably going to be limited use of it, but it could help us get to net zero energy. Challenges, there are technical challenges, chemical catalysis to improve the selectivity, formation of the carbon-carbon bonds, biological process improvements in growth, treatment, carbon-free hydrogen, commercial drivers, of course, economic value, scale, market capacity, market penetration of these new fuels, and then supporting infrastructure and technology, new supply chains, transportation, energy and material inputs, renewable energy, H2, et cetera, particularly getting biological feedstocks that aren't going to compete with human consumption, et cetera. And then let me next go to negative emissions technologies. This is something that the Academy has looked into. The negative emissions technology are best used as a component of emissions mitigation portfolio, not technologies that are deployed once society completely eliminates emissions from all transportation, electricity, industrial, and other sources. Although, of course, I don't know when we'd ever get to that point. Removing CO2 from the atmosphere and storing it has the exact same impact on atmosphere and climate as preventing an equal amount of CO2 from having been released in the first place. In some cases, deploying negative emissions technologies may be cheaper and less disruptive than the actual emission reduction, particularly in difficult to reduce sources, such as those associated with aviation, heavy industry, or agriculture. Now, this figure shows the potential role of negative emissions technologies in reaching net zero emissions. How large the negative emissions technologies need to be to meet the Paris Accord targets under this scenario shows, you show the red line of what greenhouse gas emissions would have to follow to stay below 2 degrees C. The yellow line shows the business as usual curve. The green area shows what we might be able to mitigate in terms of greenhouse gas emissions. And the area between that green area and the red curve shows what we might have to further mitigate using net zero emissions technologies. And it shows that the amount of that grows from a small wedge in the 2030 to 2040 area to a larger wedge out towards the turn of the next century. And those wedges are 10 gigatons of CO2 per year by mid-century and 20 gigatons CO2 per year by the century's end. So here are some types of negative emissions technologies and their potential. Coastal blue carbon, accelerated chemical weathering of rocks to store CO2, direct air capture of CO2, biomass energy with carbon capture and storage, afforestation or reforestation, and soil carbon capture. All of these are covered in Academy reports. Okay, and then let me go to game changers in institutions, people, and processes. As I've said, some of these are some of the harder things to do. We need new coalitions built of voters and consumers who demand low carbon lifestyles that also deliver health, safety, and opportunity. We need continent-wide transmission investments to build renewables to demand centers, to bring them to demand centers, a circular economy in carbon and all other materials, and fossil fuel dependent communities. We somehow have to deal with them. We have to give them other kinds of economic opportunities. Now, the new coalitions. Climate change, Climate change will impact all people on the planet, and the most vulnerable will suffer the most. People continue to want light, warmth, cooling, and work that energy provides, but new coalitions are building that tie together energy access and affordability for all, people's health and livelihood, and the environment. So let's look at the problem of the transmission. The location of renewable energy and generation facilities depends on where the sun shines, where the wind blows, where geothermal energy is, etc. But renewable energy without storage can't be turned on and off. So balancing renewable electricity supplies with demand loads can be done with energy storage, with improved forecasting, and with transmitting power over long distances. So this just shows where the transmission lines are right now. There aren't a lot of them, but also where we have various kinds of energy, where the biomass is, where the wind is, where solar thermal is, where photovoltaics are, tidal energy, hydrothermal, etc. And really, on nationwide, we have a lot of renewable energy in different parts of the country. So how do we balance it? So if the wind is blowing someplace, but the sun isn't shining somewhere else, we can get energy from where it's being created to where it's needed. So high voltage converters and lines can transport power thousands of miles with limited losses. Transmission helps balance disjointed electricity supply and demand, but interstate transmission projects have been politically challenging. Long distance transmission facilitates critical movement for decarbonized electricity. But as I say, it's been hard to do. Transmission planning is federal, but authority to site and build the lines typically lies with states. There have been difficulties with cost sharing as well. Interstate transmission projects really have to be dealt with in order to move this decarbonized energy. You can see that there are very few in the West where we have an abundance of low carbon energy. Now let's go to the circular economy and carbon. Of course, a holy grail is to find reuses of carbon. The current process, which is shown in the gray line, follows a take, make, use, dispose, pollute model. We take the fuel, we make something out of it, or we use it, we dispose it, and we have carbon pollution. A circular economy would reduce or eliminate pollutants, including emissions, by recycling them and making something else, using it, reusing it, remaking it, recycling. New technologies, processes, and institutions will be required to make that circular economy. So this comes from a recent report from the academies to identify the status, barriers, and opportunities for commercialization of technologies that utilize carbon dioxide waste gas. Promising areas include mineral carbonization and chemical and biological conversion. So mineral carbonization would include, for example, cement that is made from a waste CO2 stream, or chemicals and fuels that are made from waste CO2. That in the case of construction materials, it would be sequestering CO2 in long-term buildings. But of course, there are unique challenges for resource extraction depending rural American communities. There's a tax base from coal generation in the West that can result in huge tax base loss for rural communities. We need to consider fiscal policy reform to address the failings of current business models, regional and multi-sectoral coordination to reinvent the urban-rural social contract on energy service, and how to re-envision rural economic development through developing robust institutions, resilience, and useful infrastructure, rather than simply replacing old energy technologies with new ones. We can't solve the climate energy problems unless we solve it together. We need to make the solutions about jobs, about health equity, about environmental justice, about access to quality of life, and a future for everyone's children. Because these are values that everyone can agree upon. And if we bring everyone together into the discussion, we're much more likely to make progress on this. So with that, I will be happy to take questions.
Thank you. Do we have Dr. McNutt on real audio live here? It looks like we do. So
I am here. Good to see you, Michael.
Okay, welcome. Thank you for that inspiring presentation. We have a couple of questions from the Q&A stream. Let me start off with this one. How do we make the business case for transmission investments, especially when many utilities have been focused on non-wire alternatives and looking more towards enhanced local balancing? Or interstate investments, do you see any lessons we can use from the gas pipeline infrastructure to help inform the approach to long-distance electricity transmission?
Right. So I think that it shouldn't be an either or. I think that local investment is perfectly a good solution. For example, I'm speaking to you right now from my home in California, and we have solar panels on our roof, and we're very happy that we can be pretty much net zero in terms of our power use here. But nevertheless, I know that that's not possible for every person depending on their power use. So I think that we need a mixture of both. And I'm perfectly happy with the fact that my solar panels are actually connected to the PG&E grid. And the fact that they are means that on a very sunny day here, I produce too much power, and it's sent to the Central Valley in California, where they're cooking hot and they need it for air conditioning. And then in the winter, when I'm not producing as much power, I get power off the grid back here. And so I don't, so that makes me net zero for the year. So I think we do need transmission as part of even our net zero, even if I can produce it locally. So it's back to that, argument that even if you can produce enough power locally, you can't produce it at the rate you need to every day at the right amount. There was an interesting paper that was published in Science magazine when I was editor-in-chief there by a number of experts who showed that using renewable energy in the United States, mainly wind and solar, if you had transmission lines, you could produce enough power to meet the needs of the US as long as you could get it to where it was needed to balance out the fact that the sun was shining in different amounts at different places and the wind was blowing in different amounts in different places at different times. But it all depended on moving the power around from where it was available to where it was needed. So, you know, I think we do need to have a lot of local generation, but we also need to move it around to balance that load.
All right, thanks. It is a real problem to get it through states that don't really need it. So for example, right here in the Northeast, we're trying to get Canadian hydroelectric power down to New England, and it's on the ballot now in Maine. It may be blocked by the voters of Maine because it doesn't do them as much good as it does.
You know, Michael, they might take a page out of what I saw one of the New England states do. In fact, it might have even been Massachusetts when there was some objection to windmills offshore. Was they offered reduced power rates, reduced electricity rates to those who felt that they were going to be adversely impacted. And so you provide incentives. So let's suppose you're in a state like Nebraska, and you don't want this big high voltage power line going through your state. But as a consumer, you're going to be offered far below market rates for the electricity that would come from those power lines. That could be an incentive for the consumers to say yes to that power line.
So getting the incentives right then is an important part of making this work.
Yes, yes, I think so.
Another question. How do you reckon the costs for nuclear waste disposal and storage over 1 million years when you're evaluating the cost of various low carbon electricity generation technologies?
So I think we have to take into account that any energy source has drawbacks and has waste problems. Look at photovoltaics. I've seen a number of concerns raised lately about the looming waste problem that's going to be coming from photovoltaics, of all the waste from discarded photovoltaics. And of course, the same with nuclear. One thing I didn't mention about the next gen nuclear power is that many of these reactors are being designed to actually burn nuclear waste. So they take what we have classified in the past as nuclear waste, and they use it as their fuel. Now, that doesn't mean that what is spent afterwards is still benign. It's not, but it takes it to a much lower level. So I think in the design and execution of all of these projects, whether it's the blades for wind power, whether it's the photovoltaics for solar, or whether it's the ultimate waste that comes from nuclear, we have to build in the safe disposal of any waste products. And in fact, part of the innovation needs to be, what is that circular economy for that waste?
Thanks. Looks like we have time for one last question. In what areas is the U.S. underinvestment in decarbonizing its economy significantly bad right now?
Well, I would say that we have a lot of good research going on that is, the early phases, but where I see China leaping ahead of us is they have these 40-year plans where they are able to take good research ideas and work to implement them and build the political and they don't have to deal with getting social acceptance, that sort of thing. That I won't actually say that that's necessarily a advantage. I think the fact that we do worry about social acceptance is a good thing. But we are not moving ahead as briskly with the business side of renewable energy, and we're actually spending a lot of our political capital propping up the fossil fuel industry at a time when we're not, when we should be investing in a renewable energy future, because I think that's where the jobs are going to be. I think that's where the big investment opportunities are going to be, but we don't really have a level playing field for them here in this country.
Well, thanks so much for being with us. We now have a 1 hour and 5 minute lunch break. We'll convene at 1:10 Boston time.
Yes, I'd like just to thank all the morning speakers. And of course,